morphisms are what we might call translations between type series. Maybe, yeah, translations, or you might, well, maybe I won't mention this before. Maybe by translations I mean something like compilation or translation. Okay, so those are all the examples. Let me now give the definition of a category. Like I said, it's basically what I wrote over there, plus some extra structure that all of these examples will also have. Of course. So, definition: a category C consists of a collection of objects. So I guess I'm also defining the word object now in this definition. So a collection of objects that we call OBC. And for every pair of objects, X and Y in OBC, we have a collection of morphisms, or you can also call them maps, or you can call them arrows, that is denoted com xy with a little c here. Okay? So when we're just talking about one category at a time, we'll probably not write this little c. But when I start talking about two categories at the same time, then I will write the little c and maybe also a little d to make clear what category I'm talking about. Okay, so I want to say that, we go right on it forward. So I don't want to erase all the examples we go right on it forward. So here's a notation. When we have an F in com xy, maybe I should also point out that the objects are usually going to denote with uppercase Roman letters, and the morphisms are going to denote with lowercase ones, so usually like x by z, f to h. But maybe when I'm talking about a particular category, it will be more appropriate to use some other. This? Yeah, so this is my category C. So sometimes I'll talk about two categories, and then it's necessary to have this C here, so you know what we're talking about. Okay, so when we have a morphism F from X to Y, we write, we can write this if we want, but we usually write, and I will write in these lectures almost always, F from X to Y. That's how you read it, so F from X to Y. Okay, so that's notational aside. So these two things are maybe like the real data or something. I'm going to give you more data, but just the next two pieces of data are operations on these underlying sets. So we have some, well, underlying collections, I should say, or bigger sets. Now I'm going to give some operations. So for each object X, a morphism id X, so the id stands for identity. It's very common also to write one sub X. If I do that, maybe you should complain, and I should be consistent and write id X. So we have a morphism id X from X to X. And for each pair of maps that are going to have something in common. So what do we mean by this, I'm maybe suppressing some extra entities. I mean, for each triple of objects, x, y, and z, and for each pair of morphisms, the first one's going from x to y, the second one's going from y to z. Maybe I should correct it, so let me go on. A composition that we call G circle F from x to z. So if you have some way to get from x to y, and a way to get from y to z, then you can go step by step and get from x to z. So we call it the composition, and know very well the order here. Okay, so kind of, I'll list a little bit better. But it comes from the fact that if you have two functions between sets like this, so if we're looking at the category of sets as an example, and you want to think about what this composition means, G circle F, what it's going to mean is that if you plug in an x, so in the category of sets, if you plug in an x, it's going to be G of F of x. Right, so if you want to first do F and then do G, and you're talking about functions, usually write it in this order. And backwards. So the first one is on the right and the one on the left. Okay? Okay, so this is the composition, and I will give this a name. So let me call it the identity morphism, as I said, such that maybe I'll use this example. How do we want to use this again? Okay, so we have these four pieces of data. So we have these two things are giving us a bunch of collections or sets. These two operations, and now two axioms. So such that we have that the identity behaves like identity with respect to composition. So for any f from x to y, for any x and y, we have that if I do the identity on x, and then I do f, that is equal to the to f, first of all, which is also equal to first doing f, and then the identity on y. Yes?
If there are many arrows from x to x, is only one of them the identity? Are they all the identity? Or?
Yeah, so the definition says that for each, so it consists of these things, and the third thing is an identity morphism, a special identity morphism, so this one. It could all, well, it depends on what kind of category you're talking about. So for instance, in the category of sets, only one thing is the identity. But it could be that other things behave in the same way in other categories, like other morphisms might behave in exactly the same way as the identity, but not just be the special identity. Yes?
This may be for later, but we can defer it. But I saw something about left-sided or right-sided identities, and I know this is just a quick overview for now, but would you be able to speak to that? Like the notion of identity, like a left-sided identity and a right-sided identity, and somehow this makes a...
Yeah, so we're asking that these identities are left and right identities for composition. Try to think if so definitely like people invent different notions, like different mathematical notions that are related to categories. So for instance, someone asked about double categories. Double categories are things that aren't exactly categories, so they're something closely related. And I'm trying to think if I've ever heard of something like a category that only had that the identities are like left identities, or that there's separate left and right identities. I don't think so, but I think that maybe I've read some papers from the 50s around the time that they invented categories, and maybe Ariston, a guy called Ariston in particular, defined them in a very strange way where he had separate left and right identities and then showed that they were the same. Yeah, but it could happen that someone invents a notion of category that only has left identities, or only has right identities, or only some of them. Sometimes it's something, but I don't know about that. Yes?
So are the identity arrows for different objects, are they the same or not? I guess what, or is it like not meaningful to different concepts?
Yes, very good question. So, yeah, the way I want to set it up, yeah, other people have done, I mean, other people at the very beginning of the invention of category theory in the 50s were doing kind of crazy things. But nowadays, we say that the homomorphisms are like a bunch of different collections or sets. So hom xy or hom xx is one set, and hom yy is another set. And the identities, they live in these different sets. And I'm going to put out a category theorist. I'm also a type theorist. So I really, you know, when two things have different types, they're really different, right? So we don't want to conflate two things that have different types. We want to like what's similar. Yeah.
I'm going to ask a follow-up. Does that mean that they're not equal, or it's not meaningful to ask whether they're equal or not?
It's not meaningful. Yeah. Yeah, I would say that's a particularly type theoretic perspective to have. Okay. And maybe now that I've brought up type theory, I would say that this definition is particularly well suited to write down a dependent type theory, like what I'm telling you about. Because we have, like, for every x and y, a blah, blah, blah. For every x, y, z, f, g, a blah, blah, blah. That's a very type theoretic thing to write down, but I'm just going to write down to not make a lot of dependency on other sources. Okay, so we have this, and we have another law that we want. This one's a little bit more complicated. So for any f from x to y, g from y to z, and h from z to a, we have now these three things. So when two morphisms like the f and g up there share a y, I will say they're composable because they have the right kind of situation to be composed. So now we have three composable maps, right? These two guys share a y, and these two guys share a z, so we have three composable maps. And now there are two obvious ways to compose them. We can do, we can put f and g together first, and then compose them as h. Or, well, maybe I can write the equal sign yet. Or we can compose first the h and the g together, and then compose with that. Maybe there's something kind of similar happening in Delia's lectures, with the way to kind of conjunct things. But in category theory, we don't want to say these are different, they're the same. So we have three composable arrows, there's just one way to compose them. Either of these ways are the same. Yes?
Is H going from Z to A, or
Yes.
it's not X?
No. So it's just like a line. Like
Oh,
X to Y, Y to Z, Z to A.
Okay.
Okay. Good question. Okay, so we have these axioms. Now I want to go back to my notation board. I'll erase this. 1 second, please. Okay, so in category theory, the whole subject, so there's a particular style of doing things. And one thing that we like to do as category theorists is draw the arrows out. I've been drawing them in the air, kind of, because I want to wait till this moment to start drawing them on the board. So we argue in category theory, or category theory CT, via diagrams. Maybe not always. Sometimes it's easier to write things in this way, but usually you want to see a diagram, so it's easier to read most of the time. So let's look at these two equations. F composed of the identity and the identity composed of F are both equal to F. It's a bit easier to read if I draw out F and the identity. So the first one says that if I do the identity on X, and then I do F. That should be the same thing as F, that equals F. Okay, so I've drawn these three arrows, matching up with their, the objects that they're coming and going from. And what we say when this path, like the composition of this path, equals this path, we say that this commutes, and we draw a little circly thing. So we say this commutes when the composition of the two paths, so there's always going to be like a die where all the arrows are coming out of it, and a die where all the arrows are going into it. And there's going to be two paths from the first die, the die to the last die. And when the composition of those paths are equal, then we say it commutes. So in this particular case, this diagram commutes when these two things are equal, which they always are in every category, so that's a trivial thing to say. And we sometimes draw this circle. So I'm drawing it now to be really emphatic that it commutes, but often in the rest of the lectures and in category theory, you don't often see the circle because kind of just by drawing a diagram, you're kind of just saying it commutes. But if you want to be like really emphatic that it commutes, you can draw this little circle. Okay.
Sorry, so the circle is just emphasizing that this path is the same morphism as this path.
Yeah.
Okay.
Yeah, you could also draw an equality. Right. Maybe that makes more sense, but this is what's used often. Yes.
I've seen commutative diagrams with different contexts, and so are we saying, like, are we defining commutes based on just ID, or like, is there like different diagrams we can draw that
Yeah.
don't use it?
Yeah, I'm just talking about this one example.
Okay.
Let's see. I want to go back to, no, I don't need this anymore. So, oops. So, to draw one that's like more arbitrary, let's say, I could say that I have 4 objects and 4 arrows, and now this commutes if this commutes if G circle F equals I circle H. And of course I could have like, this is where I could have like a pentagon, I could have something with like many sides, and often you also see something like diagrams that have multiple tiles, like this. And then we say this whole thing commutes if this tile commutes and this tile commutes. Which maybe is a good exercise, implies that then also the outside commutes, in the sense that this composition is equal to this composition. Yeah, so we can have like shapes. What is it called? Just, I don't know, a shape with however many edges you want. I'm reading the first grade edition is kind of often. Sorry? A polygon, yes. A polygon with however many sides you want. And then we can stick the polygons together and talk about the whole thing. Yes.
So we could think of a commutative diagram, at least in the examples we've seen so far, as kind of like generating a category inside your category, right? Like I'm taking some specific objects, I'm taking some specific arrows between them, and I'm saying, okay, what category does this generate? And I think the commutative diagram commuting is equivalent to saying, like, every constant I put a 0 with one thing in. Is there any case where that sort of doesn't work?
I mean, I guess just to find a counterexample, I could, what do I want to say? I mean, I'm not sure what you're thinking of maybe, but maybe I could do this. And then I have,
Oh, if you repeat an object. Okay.
Yeah.
Yeah, that would make it, yeah, okay.
okay. Yeah, okay, so I have this sort of commuting diagram, and this is often easier to read because, let's just say, this kind of equation has some information in it, like the names of all the arrows, but it doesn't have the names of all the objects that are involved. So there's less information in this equation. So it's kind of, you have to like remember, okay, f goes from x to y, and this kind of goes from x to x, and fill in some of the blanks. Sometimes people do use equations because sometimes you have like some axioms for your category written in equations, and then you can just, if you have a long calculation, you can just check line by line that you're doing the calculation correctly. But for our kind of understanding, we use right diagrams. I want to say that so this is the most basic kind of diagram in category theory. There are other kinds of diagrams. I want to say, just very briefly, that there is something called string diagrams. And I want to mention them because they're very, very, very similar to the proof nets that we were talking about in the morning. So they're very similar to proof nets. Okay, I think I'm just gonna stick with regular diagrams. Okay, so I now want to give, or look again at the examples and verify with you that they do form categories, because when we gave the examples, we didn't have the full definition of category. So, okay, our favorite example set in this category, and all these are categories, otherwise I wouldn't have told you about them. So the collection of objects are sets, as we said. Now here I was vague about the morphisms, they're functions, but what I want to say is that com x, y, for any two sets x and y, is a set of functions from x to y. Now we need a particular guy in x, from x to x, and that's going to be the identity function. Okay, like so in lambda notation, we have, so right here, the identity, we can write as lambda x dot x, going from x to x for a particular x. And composition, I did already write it and erase it. So composition, if we have one function from x to y, another function from y to z, functions in sets are just defined by where you send the elements. So we want to send an x to g of f of x if we're going to compose f and g. Okay, what other examples do we have? Okay, so prop, its objects are compositions and the morphisms are implication or derivation. What is the identity morphism in prop? What do you guys think? Yes?
It'll somehow correspond to the fact that each proposition entails itself.
Yeah, exactly. Yeah, so usually in a logic you have some rule that says from P you can divide P. So that will give you an identity. If you don't have that rule in your logic, or that's not somehow provable from the other rules in your logic, then it doesn't form a category. So we definitely need that kind of thing to form a category. And what about composition? Yeah.
Transitivity of the consequence relation.
Yeah. So it's a good idea now to think about where do I have composition? To think about composition as something like transitivity. Okay, so if you have that x is less or equal to y, and y is less or equal to z, you know, in the real numbers or something, then x is less or equal to z. Okay, so it's something like transitivity. And indeed, when we're looking at some kind of logic, and we form this category prop from that logic, if x implies y, so x, y, and z are propositions, if x implies y and y implies z, then indeed, usually your logic will allow you to then prove that x implies z. If it doesn't, then it doesn't form a category, and that would be weird. Okay, so for types, the category of types is pretty similar to the category of sets. So the identity and composition, we've actually just write down in the same way. We get an identity morphism from x to x. We just take lambda x dot x. And in the composition, we have this lambda x dot g of x. We compose f and g together. Okay, so for group, we have the identity function between two underlying sets of of one group to itself, does happen to be a group homomorphism. And if you compose two group homomorphisms as just functions, it will turn out to be a group homomorphism again. So this guy basically inherits identities and compositions from the category of sets. Those are all of these are sets of some extra structure. Similarly here, and I guess the program specification is basically the category type, so it's similar. Okay. So maybe there are usually two patterns to what identity and composition look like. Either the category is, the morphisms in the category are kind of determined by where elements of the objects go, like this, and then we can define identity and composition like this. Or we have something more like logic, like prop, where those things are given axiomatically. Okay. Maybe we can think real quick about our two laws, the left and right identities and the associativity. The first was a question, I think. Yes.
Yeah, so since we're talking about groups before, is there a notion of anti-commutativity in category theory?
No. So maybe you can invent it, or maybe somebody has invented it, but I don't know about that. Yeah. Okay. So, right, I wanted to talk about, so we verified that everything has identities and composition, but what about these two rules, these two axioms? Okay, so I think it's pretty easy to verify that if you compose with the identity on one side or the other in set, you get the same thing, actually the setting axiom itself. And similarly, composition is associative. So if you think about H, you just, wherever you put the circle, it's going to turn out to be X of G of F, sorry, H of G of F, okay? So for prop, this is a category that's a little bit different. It has these two identities for maybe some interesting reasons, but one like particularly all-encompassing reason. And what is that? So here I wasn't very precise about what the morphisms are. Let me be a little bit more precise now. Let me erase this. So to be more precise, in prop, we want prop PQ to be what? So this should be a collection, which is my word for set. So I don't really want to say set. So it gives me a set. So I want prop PQ to be some particular set. Up there I said it was derivation or implication, which is a little bit vague and maybe doesn't exactly spell out what set I'm thinking about. So let's say that this is singleton. I don't know, just call the inhabitant true for fun. Thinking that's a good idea. Why not? So let's call it true. If P implies Q, and I'm going to say that it's the empty set otherwise. So this is a special kind of category called thin. It's not an important word, but in case you're wondering, it's called thin because the Hom sets have at most one element. So either there just is an element, it's just saying, yes, P implies Q, or no, P doesn't imply Q. So these are basically like acting like the Booleans. Yes, P implies Q, or no, P doesn't imply Q. Okay, so now, if I look at these equations, bring this down. So whether or not these things are equal to each other, each one of these three things is definitely a morphism from X to Y. Because F goes from X to Y. And here we have something from X to X, and then from X to Y. So this goes from X to Y. And here we have X to Y to Y, so this also goes from X to Y. Okay, so here we have three morphisms from X to Y. But in our category prop, there's at most one morphism from X to Y. So if we have 3 of them, they have to be equal. So for a very trivial reason, we have this law in the category top. And similarly here, both of these morphisms, whether or not they're equal, they're all going from X to A. And in this particular category, there's at most one morphism going from anything to anything. So there's at most one morphism going from X to A, so they have to be equal. Yes.
So, these are easy because it's in a category. If you have a category that's not in, but where the composition is a little weird, you could have like all the dots and all the arrows in the right places. If the composition relates the wrong arrows, it won't be a category.
Yeah.
Okay.
Yeah, so I would say that if you're trying to define a category, like this would be the part where you might fail. Like you kind of arrange everything well, and then in the end, do they match up? Could fail there. Yes.
This goes back to when I was asking about the left-sided versus right-sided identity. I noticed you had ID sub X on the left and ID sub Y. Is there any case where that would not be an equality, where you would only have an identity like ID sub X, but you couldn't get it on the other side?
So we always have these two equalities because it's part of the definition of category. So we always have it in category theory. So we would just require that for categories. But like maybe you could invent a related notion, or it doesn't hold.
I'll ask afterwards because it's related to like a bijection or what is it, automorphism? And it was something related to that. It's from one of the old category textbooks. I'll do that.
Okay, thanks. Yes.
I want to say there's a proof of two-sided identity. Left and right is equal to regular identity in the slide channel. If you want to look under.
Okay, thank you.
Yeah, that's also true. Yes. Yes. Any other questions? Okay. So, what time is it? Okay, I have 10 minutes left, right? Does anyone have any burning questions, or did you already ask them? Because otherwise, if everyone already asked questions, maybe we'll say a little bit more, or otherwise we can just have a question session. Yes.
I don't know if I got this correctly. You were talking about bin categories before. Is that the word you used?
Yeah, then.
Yeah, I'm not sure I got what that was.
So it's not very important,
Okay.
but that is a pretty obscure word actually. But if a category has a property that every Hom set, so for every PQ or X and Y, PQ has at most one element, then you call the category thin.
Oh, okay.
Yes.
Like the collection of morphisms, like homomorphisms EQ, is going to be non-empty if and only if the like proposition P implies Q is also like non-empty, like it has like sort of proving it.
Yeah.
Okay, so they're like related in that way.
Yeah. Yeah. Okay. Maybe that's the starting to the question session now. So I would just say something like not very crucial, but maybe something kind of interesting. So for